Okay, this is chapter 1, sampling and data. Now we want to start when we're doing a statistics class, which is figuring out what statistics is. And statistics is the science of data, in particular, the collection or gathering, analysis, interpretation, and presentation of data. Basically, we will want to answer some kind of question. Who is going to win this election? Or how much do students spend on books each year? We will find some way to gather data from all of the different people that are involved in this question. We will analyze the data, doing computations, doing calculations on that data. We can present the data with a graph, and we can interpret that data into a story. There's two different types of specific statistics that we're going to look at here. We've got descriptive statistics and inferential statistics. Descriptive statistics is all about the numbers. We're going to organize the data, summarize the data. That's all the computations, all of the equations, all of the graphing. Whereas inferential statistics is all about the words. Based on all of the data we've gathered, here is our result. Combining these two pieces of statistics together is going to be our focus in this course. Before we can jump into actually doing any math, we need to understand a lot of terms. And so at the start, we're going to talk about what we're trying to determine something about, which would be the population. The population is the entire collection that we are trying to study. We're trying to determine the winner of some election, and the population would be everyone who lives in the country or the state or whatever people are allowed to vote in that election. Now, it's not feasible to ask every single person in the country who they're going to vote for. Not everyone's going to vote. Everyone might change their vote, and for the most part, that's just too many people to ask. You can't get a survey out to that many people, and most of them probably won't respond. So what we do instead is we take a sample. A sample is just the portion of people that we collect our data from. It might be a mailed out survey, it might be phone call, an online survey, an email survey. There's a whole bunch of different physical ways that we can get the data from people. And the sample is all of the people that are actually included. So not just the people we send the emails out to, but the ones that send them back, the ones that we actually get some information from. That information that we do get from them, we can combine into a statistic. A statistic is some number that represents a property of the sample. For example, we emailed a bunch of people and 600 of them responded. And of those 600, 60% said they would vote for candidate A. 60% would be our statistic there. It's the number representing the sample. And that number, hopefully, corresponds to the whole population in some way. It's not going to be perfect because we didn't actually ask everyone. We just asked some of the people, but hopefully it's close to the real number. And that real number, the true percentage that would vote for candidate A, that's the parameter. So, in other words, the parameter describes the population, whereas the statistic describes the sample. We would hope that our sample is good enough, close enough to represent the population, that the statistic is very, very close to the parameter, and we can make claims about the population by using the statistic. But this isn't always the case. Now, the statistic and the parameter is something that will apply to the whole sample or to the whole population. But if you're just looking at one individual member, we're looking at a variable. A variable is a specific thing that can be measured. That can be the height of the person, whether or not they'll vote for a certain candidate, their favorite color, how old they are, what their birthday is. Anything that you can measure from each individual in the population, that specific characteristic is the variable. And we'll typically define a variable as x. So for example, we might say let x equal let's say the height in inches. We don't have to use X specifically. We can use any letter, but note that we use a capital letter here. In this instance, when we're defining the new variable, we use a capital letter. A little variable, a lowercase letter, might be a specific measurement. So for example, X is equal to 73. Variables don't have to be numbers like they do in a more traditional math class. It's perfectly okay for a variable to be a category, like favorite color or favorite sports team. In this case, we will say that it is a categorical variable as opposed to a numerical variable. Numerical variables are often more useful because there's a larger degree of computation we can do on them, more equations that work if we're dealing with numbers. But there's no reason we can't do some stuff with categories. So we're going to focus on both in this course. The individual values that those variables take for individuals of the population, that will be the data. 73, for example, would be a piece of data. Let's go through one example to talk about how we can get these terms lined up. So our goal is to learn the average amount that first-year students at New River pay for textbooks. We randomly sampled 100 students who are in their first year. You were one of those students that we sampled, and we found that you paid $77 on your textbooks. What we want to figure out is what all of these different terms mean in this specific example. So here, the population, that will end up being all of the first-year students at New River. Everyone that we are trying to figure something about. But it's not reasonable for us to ask every single student. Many of them probably won't respond to the survey. And so instead, we took a sample, which is just the 100 people that we actually asked. The parameter is what we're trying to determine, the average amount that all of the students, the whole population, spent on their books. But we're not going to measure the parameter, we're going to measure the statistic, which is the average value calculated from our 100 student sample. The variable would be the amount of money spent by a single student. For example, we might say more formally, let X equal the amount of money spent by one first-year student at New River. And the data is the actual amounts of money collected from an individual student. For example, the data that we collected from you would be $77. Now we can further break up data like we broke up variables into different categories. We've got here qualitative and quantitative data. Qualitative, and you can think here quality, describes some characteristic of the thing, not a number, but a category. The quality is blue. Their team is the Yankees, whatever. That will determine the categorical variable. Whereas quantitative, you can think here, quantity is a numerical data. What is the quantity of their height in inches? It's 73 inches. It's an amount of something. And when we're dealing with a number, we can further break it down into two additional categories, discrete and continuous. And the difference here is how small are we allowed to break up this data? For discrete data, there's a certain limit to what kinds of numbers it can take on. For example, if I was saying, I would like to count the number of phone calls that I make in a given day. Doesn't really make sense to talk about half a phone call or 0.7 of a phone call. You have a whole number of phone calls. Even if one is shorter than the other, they're still all phone calls. And so you're just counting up the whole number. Because we can't have a half a phone call or 0.7 of a phone call, that's what makes it discrete. And most of the things that are discrete are going to be things where you're just counting up how much of something there is. It doesn't have to be counting how much of something there is. It just has to have a limit on what the numbers could possibly be. For continuous data, this now can take on any value in a given range. And the reason we say in a given range is because sometimes it doesn't really make sense for the data to be negative. And so we still want to be able to say that the data is continuous if we're measuring something like height, even though it would make absolutely no sense to say -3 inches tall. But I've been saying 73 inches. There's no reason I can't have 72.5 inches or 72.7143 inches. There's no amount of decimals that I couldn't add on that could exist as a possible height. Sure, it would be hard to measure that amount of precision, but that measurement would make sense if I could get it. And so this is what we mean when we say quantitative continuous data. Any possible value in a certain range can exist. It's the difference between, for discrete, having only a bunch of possible numbers, and for continuous, having a start and an end that makes sense, but including all the numbers in between. Let's switch gears a little bit and talk about different types of samples. The question here is, how are you going to get your data? It's not reasonable to ask every single person in the population, so we'll have to choose some. The simplest way to do this will be a simple random sample. Take every single member of the population, determine how many we want. There are 300 million people in the US. We need a sample of 1,000. So we're going to randomly choose 1,000 people. Maybe we'll pull names out of a hat. That wouldn't really make sense for putting 300 million names in a hat, but that might make sense if I was doing, say, a sample out of the students at New River. That could be feasible. Maybe we take the last census data and we assign every single person a number, and we randomly choose 1,000 numbers, and we send each of those people a mail survey. Or maybe we send out 10,000 and we take the first 1,000 that we get back. Something where there's no rhyme or reason to how we're doing. We are completely and utterly randomly choosing the number of people that we want. Now, there's a couple of issues with a simple random sample. Number one, it can be difficult to actually do a simple random sample. If, for example, all of the people that you are trying to survey, suppose it needs to be a door-to-door survey instead of a phone survey, because we need to do some back and forth in person with a form and with talking. Well, it would be difficult if we had to go to, 1,000 people, and every single one of those 1,000 people lived in a different town. That sounds really complicated. Also, just because of how random it is, it's very likely that we might purely by accident do exactly the opposite and mess up our data. For example, maybe by chance, we accidentally only ask male participants, or participants that live on the West Coast, or participants over the age of 55. Or it's disproportionate, that number. Maybe it's only supposed to be 10 people, 10% of the people that would be over 55, but we accidentally got 50%. That will definitely mess with our results. If you do it simply randomly, it won't always go that way. Of course, on average, it will work out, but every once in a while, it doesn't work out. And we might want to control for that. And so for this reason, we're going to give ourselves several other different ways to sample. The first here is a stratified sample. A stratified sample is trying to correct that issue where you might accidentally mess up and get too many or too few of a certain group that you expect behaves differently than the average. What we're going to do is we're going to divide the population into those groups. Let's roll with that age thing. Suppose that we wanted to sample 1,000 people, and we're trying to deal with different age groups. So maybe we have an 18 to 25 age group and a 26 to 40 age group, 41 to 55 age group and a 55 plus age group. And we believe that each of these people are going to answer our question differently. Perhaps this question has to do with minimum wage, for example. And people under the age of 25 are more likely to want a higher minimum wage because they're more likely to be on a higher minimum wage, as opposed to those above 55 who, on average, have been working their jobs longer and are less likely to be on minimum wage. So we think that these groups are going to answer differently. Therefore, we want to make sure that we get a good chunk of each group. What we're going to do is we're going to sample individually out of each group. We'll take a simple random sample of each so that they are proportionally the same. So for example, let's suppose that we're trying to get 10%, and this group makes up 20%, this group makes up 40%, this group makes up 15%, and this group 25%. Well, then we might go ahead and sample 2% here, 4% here, 1.5% here, and 2.5% here, which adds up to a total of 10% of the whole population. And yet, if we randomly did 10%, we may have messed up. We may have gotten too many 55-year-olds, not enough 26-year-olds. It's very important sometimes that you account for these different things and you sample accordingly. So again, with the stratified sample, what you're going to do is you're going to break the population into groups that you think might influence the results, might influence the data, and sample proportionally from each group. The next type that we're going to talk about is a cluster sample. This is a way to sample rather than trying to make the data more authentic, but to make the gathering process easier. What we're going to do is we're going to divide the whole population into clusters. We're going to randomly select some of those clusters and sample every member from that cluster. For example, let's suppose that we wanted, in our example, to sample 1,000 people. And what we're going to do is we're going to choose some city streets, randomly select city streets. And we'll sample all of the people on those streets. What does this do as opposed to a simple random sample? Well, it means that we don't have to go to 1,000 different homes in 1,000 different towns because a lot of those homes are going to be in the same town. It makes it a little bit easier to get results. And yet, hopefully, the different individual clusters are behaving the way that we would expect the whole population to. The members of one individual cluster are not expected to act particularly differently like they were when we were stratifying. Now, let's do a visual example here to show the difference between cluster and stratify. So for stratify, in both of these examples, let's suppose we have 40 individuals. And we'll do the exact same thing for cluster. We've got 40 total individuals. And let's suppose that our goal is to sample 12 out of 40. Now, for the stratify example, let's suppose that we expect that each individual row will influence the results. but we will suspect that the column does not. So we think that based on which row these individuals are in, we expect to get different answers. But we don't think based on which column we pick, we expect to get a different answer. If we were going to stratify, what we might do is we might break our population by rows, because we want to make sure that we sample correctly from each row, because we think that if we accidentally got too many people from row 1 and not enough people from row 4, our result would be very different. And we need 12 total people. Okay, well, there's 4 rows. Let's just do 3 people from each randomly. So we might have something like 1, 2, 3, 1, 2, 3, 1, 2, 3, 1, 2, 3. We split it up based on rows because we suspected that the row might have had an influence on the result. And then we pulled a simple random sample from each row. With our cluster sample, we're going to instead break up by column. We don't actually think that which column we are in is going to have a significant result. And so we'll break it up by columns. And then we'll go ahead and we'll choose 3 of these columns, because that will give us 12 total. So let's suppose that we pick this column and this column and this column. In both scenarios, we got 12 individuals. In the stratify example, we made sure to account for the differences in rows and get an equal amount from each row. In the cluster sample, we broke it up into columns because it was just easier to pull out all of the individuals from a column. It was much faster for me to circle 3 columns than to circle 12 individuals. And because we don't think that which column you are in will influence the answer here, it's okay to do that. This is the difference between stratify and cluster. In stratify, we break up something where we think it will matter which group you're in, and then take a sample from each group, just some of them. In a cluster sample, we break it up into groups where we think it will not matter which group you're in, and then sample the whole group of all of the groups that we pick. The next type of sample is a systematic sample. This is kind of like simple random, except for it's a little more structured. Basically, we'll put the whole population in order, and we'll choose however many we need. We'll just go that frequently. Going back to our same example with 40 individuals, and we're trying to get every 12. Well, if I divide 40 by 12, the outcome ends up being 10 over 3, or 3 1/3. And so we'll say, okay, this sounds easy enough. Let's just choose every third person. 1, 2, 3. 1, 2, 3. 1, 2, 3, and so on. 1, 2, 3. 1, 2, 3. And the idea is that as long as we don't think that the order we have chosen has a super significant outcome, then we will get a correctly proportionate sample by doing it this way. Now, you might have to change the frequency up a little bit. In this case, we didn't actually get out the exact perfect number of individuals. We got 13 instead of 12, but that's okay. You know, if our sample size is slightly off of what we expected, it doesn't end up making that big a difference. The point is we chose a pattern and we stuck to that pattern. every third person in this scenario. Hypothetically, this will work exactly like a simple random sample. Usually the thing that you are choosing here will not heavily influence. If it was something like age, then choosing by age would make this more like a stratified sample, because now you're making sure that you're getting a good number of people from each age group. But in essence, this is just a more ordered way to get a random sample. Not particularly different than simple random in most cases. The final type of sample is convenience sample, and we're going to put a big no-no on this slide. You do not want a convenience sample. This is the lazy man sample. When you're taking a convenience sample, you're just doing whatever's easy to gather your data. The example here is a good point. Suppose that I'm trying to survey students who are in the school cafeteria at lunchtime when I'm trying to determine how much the students spend on school lunches every week. Now, the cafeteria sounds like a great, easy place to gather data. A lot of students gathered all in one place. They have to sit still for 15 minutes to eat lunch, so hopefully they won't mind as much if you want to sit down and ask them questions for 2 minutes, as opposed to trying to stop people as they are walking from class to class. But think about what this is going to do to our data. We're literally asking the people that are eating lunch how much they spend on lunch. We have inherently only asked people that eat lunch at least once a week. Probably people that eat lunch more than once a week if we happen to catch them in the cafeteria. We haven't asked any of the people who never eat at the cafeteria, but they bring their lunch in a brown bag. Okay, maybe a couple of people come in, but very few. Our data is skewed to be not close to the truth because of the way we took our data in. We want to avoid this at all costs, because our data, we can crunch the numbers perfectly, we can do all the math right, we can make the most beautiful graph, but if our data was gathered incorrectly, the whole study's ruined. And so we need to be very, very cautious as we're going through and sampling that we gather our data in a good way. That's all we've got for today. See you guys next time.